Okay, so here's another problem we'll work that we'll use influence lines. First, you know this beam has a uniform dead load and a single live load. So it's a little simpler loading combination. You notice there's no live uniform load. But we have two things to do. We've got to find the maximum positive moment at C and the maximum positive shear at C. So I'm looking for the moment and shear at C. So let's draw the influence lines for those cases first. So I've got a roller at A and really a pin at B. So this is really just a simple supported beam. It looks complicated, but that's really all it is. So let's imagine the first one being, let's see, A is moment. So we're going to do the moment influence line for this problem. So this will be the moment at C. I'll draw a kind of a template for that. So C will be a point of interest, and so will B. So when I imagine my hinge here and positive moments applied, Mr. Wilson, how are you?
That's wrong.
You're suited even.
I'm not. You're bearded.
Thank you. I've noticed. What are you doing here?
I'm waiting for Daryl.
Slumming?
Going to eat lunch.
Oh. Are you taking him out on the company dime?
No.
No.
Taking Daryl out. I should, though. He's getting married.
That's no comment.
He needs money. Well, you enjoy yourself.
You too. See ya. So, is point C going to go up or down? Up. So that means if it goes up, we'll get a shape like that, and then it'll hinge, and this one will come back. So we get kind of a big triangular shape. You'll also notice it's all positive. We'll come back and find this value in just a second. I wanted to, kind of in the same place, draw the shear at C. So again, there's this middle point that I want to deal with, and this is the end point. Now in that case, what's going to happen? We're going to have our, this one I did want to draw on here to help you visualize it. So we've got this kind of weird shearless connector, right? And we're going to apply positive shear to one side and positive shear to the other side. So looking at the left segment, is this point going to go down or up? Down. And then on the right segment, down or up? Up. So I'll draw that to scale. You get a shape that looks like that. Now remember, this is 1 meter, and this is 3 meters. So what does that tell me about these values here of the triangles? Well, it tells me that this value is 3 times bigger than this value. So if this is 3 times bigger than this, then this is going to be probably 3/4 and 1/4. You see that? And I'm done. But I did want to notice that we do have a negative section and we have a positive section. Does everybody see how that worked? Right there? I just want to remember, remember our change in shear is always going to be 1. So 1/4 is to 1 as 3/4 is to 3. So that's equal. Similar triangle. But I'm going to have to come back and figure this one out. So let's do that. I'm going to come back to my drawing. I'll draw a free body diagram of the structure. A is a roller, so I'll just have a single reaction. I'll call it AY. And then B is a pin, so there's technically BY and BX. Now I'm trying to find the moment at C, which is right about here. And you can see the largest value for that is when I'm at C. So I'm looking for that position. So again, this would be 1 meter and 3 meters. And I'm trying to find the moment there. So when I cut my structure to find the moment at C, you want to work the left side or the right side? Well, there's not really a clear advantage, but I'll just pick the left side. So if I pick the left side, I need to find AY. So how do I find AY for this load system? Some moments about B, right? So if I sum moments about B, set it equal to 0, then I'll have the moment created by the load 1 with a moment arm of 3 meters, and then AY creating a negative moment with a moment arm of 4 meters. So it looks like AY is going to be 3/4. So then when I come and cut my structure at C, and I know my reaction AY is 3/4, I'm looking for the internal moment at C, and I know this length of the segment is only 1 meter. What's the moment at C? Well, if you don't see it, go ahead and sum the moments at the cut and just compute it. So what would that be equal to? It would be the internal moment, which is positive. The reaction force creates a negative moment, so it would be minus 3/4 times 1 meter. So it looks like the moment at C is equal to 3/4. So that means this value here is, interestingly enough, also 3/4. There's no pattern to be seen here. It's just coincidence. Any questions about that? Yes, Mr. Brown.
Is there something that tells you that the moment at C is positive?
I just assumed the moment at C was positive, and then when I solved for it, I got a positive value.
I was wondering if the diagram should,
Well, the way I drew the diagram using the Mueller-Breslau principle, I would expect the moment to be positive. And plus, look at this beam. Any load applied on the beam that's gravity-based, this beam should all bend in kind of a smiley face, so it should be positive moment everywhere. There should be no negative moment in this structure at all.
Should that moment diagram be in meters?
It's not a moment diagram.
Or the moment thing be in meters?
The unit is, yeah.
Yeah, okay.
So this, is it in meters?
Yes.
Yeah, I lost my unit there, so this should be meters. So you're right. So the shear influence line is dimensionless. The moment influence line will have length units. So now we have to go back and solve the problem. So let's find the maximum moment first. So I want the max positive moment. So what's the max positive moment? Well, I'm looking at this. Where should I put my concentrated load of 3 kilonewtons? Probably at the maximum value. So I'm going to have 3 kilonewtons times the maximum value, which is 3/4, and that's a meter. So that's the part, this is the concentrated load. So this is the force, the live force. And then I'm going to add to it what? It's a uniform dead load, so it has to go over the whole structure. So that's going to be 0.5 kilonewtons per meter. That's 500 newton meters. And then the area of the influence line. It's a triangle, so it's going to be 1/2 the base, which is 4 meters, times the height, which is 3/4 of a meter. And that part is the the dead uniform load. So what's all that put together? Doesn't work out nice and neat, does it? You guys have to help me with that. 9 divided by 4 is 2.25. Let's see, half 4 plus. Oh, it comes out to be exactly 3?
Yep.
How convenient. So that'll be 3 kilonewton meters. So the next one asks, I want to find max positive shear. You can see there would be potentially a negative shear. I could put my live concentrated load just to the left of C and get a negative effect. Or I could put it just to the right of C and get a positive effect. So that's what I'm going to do. Now the dead load, I don't have any choice. I have to run that the whole length. And I think you can see from this diagram that the positive area is much larger than the negative area, so you can get a positive effect from that too. So again, we'll start with the concentrated load, which is 3 kilonewtons. So the maximum positive value is, interestingly enough, 3/4 again, but no unit for that. And that again is the value from the live force. And then I need the area of the whole structure. So again, I'll have half a kilonewton meter as the intensity, and then I have 2 triangles to deal with. So it'll be 1/2, and then I'll have the base times the height of the individual pieces. So the base of the negative piece is 1 meter, and its height is -1/4. And the base of the positive triangle is 3 meters, and it has a height of 3/4. So somebody calculate that for me, and I'll just quickly identify that as the portion from the dead load. Yeah, I don't know what that is off the top of my head. 9 is... What is that? That's 1/4, 8, 2, 1.5. Oh, is it 3?
I got 2.75.
Ooh, so close. Anybody else get 2.75? So the max shear at C is 2.75, and that'll have the units of just kilonewton. And in both those cases, the load's position on the structure are really the same. So we're going to have a pin and a roller. So as we mentioned before, the dead load's going to extend over the entire structure. We don't have any control of that, so the dead load is everywhere. And then we're going to apply the force component here at the maximum value, which just happens to be at the same position for everybody. So here's where my 3 kilonewton force will be, and of course then the dead load is applied everywhere, and that would be 1 meter and 3 meters. Again, I think this is a very testable problem, reasonable problem. So any questions about that?
Can you look at the last problem that we did?
The last problem? Let me stop this first.